Okay, so this is mostly a theory talk about the complexity theoretical result. So there will be no experiments, no implementations or so. And I guess that also some people here are not very familiar with the framework. So I'm mostly keeping this on a high level, trying to give you an idea of what's going on here. And so if you're more familiar with this, I'm sorry. So what's a recursion scheme? That's a higher order grammar that generates a tree. So it looks like this. So you have non-terminals, just like in context-free grammars or so on. But these non-terminals can also have arguments that are also typed. And then you can say, for example, that the non-terminal A, if you give it something, then derives something that depends on the argument. So in this case, this argument here would be a tree, and then the non-terminal does something with the tree, maybe inserts it somewhere or something like that. And then the way you derive the semantics here is by, well, expansion of the right-hand side of the non-terminals and by beta reduction. So I think the best way to show this is to give you an example. So let's take this recursion scheme here. And of course, the first step is that you derive A, C. So C is the idea here is that C is a tree constructor that is a one-node tree that is labeled by C. And but A is then a non-terminal that is parameterized in that. So of course, this is not a tree. So what you can do is we can replace the capital A by the right-hand side. And then on a sentential form, you get this here, where there's still some substitution to be had. And you can think of this as a tree that has as a root an A, which is a binary tree, and then as the left son this, and as the right son this. And then you can continue to derive, and I'm sorry this is jumping around. So if the left node, the left son of A is X, and X is actually C, well then of course you get the C, and so on. And then you continue, and what you see is, if you keep doing this, basically the upper part of the tree keeps staying the same. And then you can do some sort of limit construction, and then such a recursion scheme actually defines a tree. Or typically, you have to pay a bit attention for some special cases, but let's not worry about this. So the problem then is, the idea with these recursion schemes is that they are, for example, executions or syntax trees or something of functional programs, so where in particular, higher order functional programs where functions are passed around as actual arguments and so on. And what you want to do is you want to verify that they have some certain property or do something. And so formally, what you do is you take a parity tree automaton, and then you want to know, does the parity tree automaton, well, I assume you know what this is, does the parity tree automaton accept the tree generated by the recursion scheme? And of course, if you have an actual application, you probably don't ask the user to write down a parity automaton. You ask them to write down something in the engineer-friendly logic or something like that. So this is this problem, given this recursion scheme and the parity automaton. Does the automaton accept the tree? And this is known to be complete for k-fold exponential time if the order of the recursion scheme is k. And order here means basically how complicated can the arguments to the non-terminals become. So this little, it's a bit unfortunate here with the double dots. So this type dot here is just the type of tree. So you say, okay, as an argument, I give my non-terminal a tree. Yeah, either a concrete tree or something that at some point will be a tree. Or you can have more complicated arguments. You can, for example, have functions that consume a tree and then generate a tree, and you can give this as an argument. Or you have a function that consumes two trees and generates a tree. And so that's still of order 2, but of course you can go arbitrarily high. And of course, the price you pay for this is in the complexity of this problem then. As a remark, so this of course sounds horrible, kx time. In practice, you can often get surprisingly competitive with specialized algorithms. It's not the point of today's talk, but this is actually being used. So in order to explain to you what I want to do, let's have a brief look at, like a very brief look at how you would prove this here. And I'm going to omit lots of things. So you can reduce this to a parity game where one of the players tries to prove that the automaton accepts the tree, and the other player tries to refute that. And note that this is not the acceptance game of the automaton. Yeah? This is a different game, but the acceptance game of the automaton can be found in there. And such a position is then some term generated, or some sentential form generated by the grammar, and an internal state of the automaton. So for example, here we have some non-terminal f that apparently then doesn't have any arguments, and a state q, and ignore the thing in the middle for the time being. And then depending on what the position is, the game proceeds in 3 or actually 4 different fashions. So if the top operator of this on the left side is a grammar non-terminal, you simply unfold it. So assume that in the recursion scheme you have a line like that where you say, okay, f is actually on the right-hand side this thing here. So then the game would simply replace this to the left here by that, and then nothing interesting happens. But then, for example, in a position like this, the top operator is actually a tree constructor, and then what the game does is it incorporates the acceptance game of the parity tree automaton. So the players, for example, in this case, we would say, okay, maybe the automaton in state q, when reading in A, sends the copy within state q prime to the left, and the copy in state q double prime to the right. And then basically you split between the 2 arguments to A, and one of the players, in this case the refuter, or how do you call it, falsifier, chooses where to continue. And then the interesting thing here, really, that's what makes this complicated, is if you have an application like this, so you have H, some non-terminal, and apply to it BF, which is apparently then a tree. So how does this work? Because now you cannot simply expand or so, and of course you could expand H, but then the game would become infinite, yeah, because you can generate infinitely many different terms or so. And an idea you can have is that simply verifier proposes what the semantics, what the results of the game would be on this here, on this argument to the application. And of course there are different things they can propose. For example, could propose that the semantics behave like R, whatever that means, or that they behave like R prime, and such an object is called a residual. And then the other player has 2 options. They either buy this and say, okay, I believe that this is the case, and then the players have agreed that this is actually the semantics of the argument, and you simply continue with the operator side of the application. So you basically in this, you choose I believe or not believe fashion, you can agree on what the argument is, and then the complexity goes out of the way. Or the falsifier can actually challenge this and say, no, I don't believe that the semantics of BF is actually this R, and then the game just continues with this challenge, and the rest of the game is forgotten, and the falsifier tries to challenge this by, well, ignore this, but then they basically propose semantics to that, and then the game continues by verifying whether or not the verifier player has lied when proposing the semantics or not. So this is how this goes, and then of course you also have to deal with variables at some point, but let's not think about this. What makes this complicated is then that, of course, the game can come back up to the top here. Yeah? So this is not a reachability game, it's a real parity game, and basically from every point you can get back to a previously held position simply because, for example, you see here there's the F here, so at some point maybe this will change state to Q and then go to F. And of course, in the other cases, this can happen as well. So keep this in mind. Let me now tell you what I'm actually trying to do here. So the complexity of this problem is complete for k-fold exponential time if the order of the recursion scheme is k. And there is a result by well, Kobayashi and Ong that say if you really restrict the parity automaton or restrict the kind of property you can express basically to something that is just disjunctive, then you go down by 1 exponential. So the problem becomes much easier. And so my question is there actually some middle ground between this? Because, well, this is supposedly expensive, and this here is less expensive, but also you cannot really say that many interesting things. So can we get something that is characterized by space or not by time? And to be honest, the motivation is a mathematician's motivation. I wanted to know, is this true? Yeah, so is there a way to characterize this by space and not by time? But of course, you can also have more practical motivations. You could get more efficient algorithms. I mean, this is a lower complexity class. You go from k-fold exponential time to exponential space with k1 less. But of course, no, I'll say something on the last slide for this. And actually, there was a reviewer who pointed this out. So it's not my idea. But of course, if it helps to identify where exactly the problem becomes complicated. Yeah? Why is this k-fold exponential time? Or k-fold exponential time for k1 less, if you basically have ideas where all the steps on the complexity ladder are. And I think I actually made some progress on this just today. It was kind of, one would suspect that such a fragment actually exists because there is a connection of this framework of verifying higher order programs to another framework. It's called HFL. This is basically where you shift the higher order things on the specification side from the system side. And there's actually the complexity theoretical ladder is complete. So you have problems that are complete for k-fold exponential time, then for k-fold exponential space, and then for the next time, and so on. And there's a result that connects these two. Actually, you can translate from this system to the recursion scheme system and vice versa. So one would expect that such a fragment exists, but the question is, what does it look like? So what can we do there? And from this, basically from what has been seen before, is that the idea of tail recursion would be very interesting to see here. I would assume you know what tail recursion is at a computer science conference, but let's look at it briefly. So the recursive call is tail recursive if it's basically the last thing that happens. And the result of then the function call in which the tail recursive call happens is the result of the tail recursive call. So here are two examples. I think these are the standard examples for explaining tail recursion. So the factorial function and the greatest common divisor. And this one is not tail recursive because the result of the recursive call is multiplied by n. And this one here is tail recursive because it just says return whatever the result of the tail recursive call is. And for example, you see this pretty easily if you just try this with an example. So here, what's factorial of 4? Well, it's 4 times factorial of 3. And well, here, the GCD of 78 and 63 is the GCD of 63 and 15. And then you continue, and you see on the left side, basically the arguments or the pending operations to the result keep piling up. And on the right side, you simply simplify. And the result of this is that. And in programming, tail recursion is quite useful because things like this don't require you to keep a calling context or something like that. Yeah? You just have to remember, OK, I have to pass whatever I compute here back to the original caller, but somebody demanded the answer of that. And in this case, you have to remember, OK, the result of 1 needs to be multiplied by 2. Have to go to that, and have to go back to multiplication by 3, and so on. So you can condense the call stack quite a lot. And also, if you want to convert this recursive procedure into an iterative one, for tail recursive programs, it's actually very easy to just convert them into while loops, and sometimes even for loops. So the question now is, where do we find this with the recursion schemes? And well, this is the advantages we had before. So if you're familiar with these things, then you can kind of see it. So a recursion scheme of order k, and this parity automaton that gives you a parity game of k-fold exponential size. And if we just could convert this into a reachability game, then, well, reachability is easier than solving a parity game. So we could actually get the result in k-1 x space. So we really want to make a reachability game out of that. Yeah, and this is kind of the same thing as converting this into a for loop. And this is actually known how to do this for parity games. This is called signatures. Basically, to each parity, you associate a number, and then you have a lexicographic ordering of these numbers. And then while the parity game is being played, whenever you see a parity, the respective number is being decreased by 1, and the less important numbers are being reset. And once a player runs out of reaches 0 for their parity, they lose. Yeah? So if I'm in charge of the even parities and an even number goes to 0, I lose. So this is actually very easy to convert this parity game into a reachability game. The problem, though, is, of course, this result that reachability games are easy to solve only holds for deterministic reachability games, and these parity games are alternating. So we kind of have to get rid of the alternation in the game. There's a Boolean alternation in the sense that this is actually a 2-player game. We actually want this to be a 0-player game. And there are 2 sources of alternation in this game. So one, of course, is the alternating parity automaton, which has its acceptance game, that is an alternating game, and this handling of the applications. Yeah? And that's why I presented this briefly, this idea that if you get to an application, first one player proposes what the semantics of the operand thing would be, and then the other player can either buy this or not. It's like the fair way how to divide a cake. I divide it, and you choose which side you want. So that's also alternation. Yeah? So one player does this, and the other player has to either takes the challenge or doesn't. And how does it come together? So actually, if we make the recursion scheme tail-recursive, whatever that means, then this alternation for the arguments disappears. So look at this picture again. So here we have basically a transition for the parity automaton where you read an A, and then basically the one player decides go left, go right. And then we have this back edge here. And here we have this alternation where the verifier first proposes what the argument should be, and then the falsifier either challenges this or buys this. And this back edge here is the one that needs to go. Because this F here, that appears actually in operand position. So like as an argument to something else. And I would say this is not tail recursive. And the consequence this has is that the semantics of this residual, like of the thing the verifier proposes, that actually depends on the semantics of F, and the game would then link back up. So this edge is really bad. So if we can get rid of these back edges, then such a subgame where the falsifier challenges verifier's proposal, says, no, the semantics of that is something else, I don't believe it, then that really becomes a subgame where you cannot go back. Yeah, because this back edge disappears. So then simply the game condenses to a simpler problem. And then with some tricks, you can get rid of the alternation by simply saying, OK, the verifier decides the semantics should be this or that. And then instead of alternating, like the falsifier having a choice whether to challenge this or not, you simply go into the subgame, solve this in supposedly the space bound you have. And then if the answer is no, verifier lied, then the game ends. And if not, the game can continue here. So instead of the one player choosing, you can solve this game first. And since we don't care about time, we only care about space, this should work, yeah, because the game then becomes simpler. So this is the idea, to get rid of this recursion in operand position. That means we don't want free non-terminals there. But of course, this is really not well defined, what I just said. So of course, you cannot simply say non-terminals cannot appear at all in something that looks like an operand position. Yeah, so if you have like a tree constructor and then a few non-terminals below it, that's completely fine. And also, how do I explain this best? So you have to be a bit careful to not overshoot. So clearly, if you go back to this factorial example, the call to the factorial function was not tail recursive because it was a recursive call. But if I just pass around the factorial function for later use, that's not a function call at all. I just pass it around. So that, no, if I have functions as first-order objects. So that is fine, too. And we need to distinguish this. But the framework of the recursion schemes, as I presented it, really doesn't allow this easily. But what we can do is rewrite them as recursive lambda terms. So this is not my idea, but by Salvatierre and Walukiewicz. So instead of writing it like that, where you have the non-terminals and they have their right-hand sides, you write it as a recursive scheme, where you, or as a recursive term, where you say, okay, I have a recursion on S, well, not a trivial recursion on S, and then S is simply the application of this to that, and these are both recursive predicates. And now you can see what's like an initial use and what's a recursive call. So, for example, this A here, which would be this A here in the recursion scheme side, this is simply the whole term. It simply passes around the function. That's fine. Yeah, this is like completely closed, passing around this function. And this, of course, here just is also not in an operand position. Yeah, it is just under the tree constructor. But this occurrence of B is an argument to the other call of B. That's something you don't want to have. Yeah, this would introduce a back edge in the verification game. So if you recast the terms into this, then you can actually define tail recursion. And we say that a recursion scheme is tail recursive if, when rewritten on the right, like on the right-hand side, no operand side term has free non-terminals. That is, some things that are not under the not under such a y something term. And then you can prove that for such recursion schemes, the subgames where the falsifier generates a residual, that these are really self-contained and you can basically solve them before, like individually on their own without having to go back to the other game. So this would eliminate one source of alternation in the problem. The other problem is like the parity automaton is still has alternation. And so we have to restrict that as well. So let's just briefly. So in my framework, transition functions of an alternating parity automaton look like that. So you have a Boolean function here without negation about tuples where the automaton sends their states. Yeah, so this would be for a binary symbol, this would be for a unary symbol, and you can have arbitrary nestings here. For binary symbols, we can actually, and I restrict myself to binary just because it's simpler, we can basically define what non-alternating transitions mean. So we say a transition is branching if it looks like that, where this Q top here is a state that accepts everything. Yeah? So in this case, the verifier chooses either go left with this state or go right with that state. And it would be universal if it's just something like that. Yeah, but just the verifier plays no role in deciding what goes. The falsifier says, we go there and we go there, I choose what happens. And notice that these are kind of dual to each other. And then we call a parity automaton bounded alternation if we can partition the state set into finitely many components such that each of the sets is labeled either as branching or universal. And in a branching set, all the transitions are branching or they go to a set with lower index. Yeah, so if you want to switch, you have to pay by a descent into a lower component. And the same for the universal sets. And the idea here is that this really characterizes the acceptance game of the automaton then as a bounded alternation game, where if you want to have alternation, you have to basically go back to a set of lesser importance. And think of this as like a weak automata, but now the components are for alternation, not for the acceptance condition. And then you can show that if I want to check a bounded alternation parity automaton against the tail recursive recursion scheme, this can be actually done in k-1x space. And the idea is really that the tail recursion eliminates the one source of alternation, the bounded alternation automata eliminate the other source of alternation, and then you can make it a reachability game that is bounded alternation, invoke Savage's theorem to get rid of the bounded alternation, and there you are. And so as a remark, you have to strictly go down. You can relax this a little bit. I didn't present this because of time. So the actual thing is a bit more complicated. I also have an upper bound. I think we'll skip over a lower bound. We'll skip over that. I just show you the result. So this problem is also hard for k-1 X space. So this is actually a non-trivial construction, but I don't think I have time to show this. So yeah. So what did I do? Introduced this notion of tail recursion to recursion schemes, which I think is really interesting, and also introduced a new automaton model. So this is kind of extends the work of Ong and Kobayashi I cited on one of the first 2 slides. And yeah, found this fragment where we have a complexity that lies between k-1 X time and k-EXPTIME, which is just what we wanted to do. So there are a few things one could do. So this lambda y presentation is kind of uncommon, and usually, in particular, if you want to have practical model checking algorithms, you do it with other representations, so kind of have to translate this back. And there is some things there that I'm not quite sure how to do. And then what one should look at also is actual model checking algorithms, because right, k-1 space is less than k-EXPTIME, but of course this is kind of, in practice, often not the case that space-bounded algorithms are so much better. But actually, there is precedent that for this HFL framework I mentioned earlier, there are advantages if you go to this space-bounded framework in practical terms, just because it's easier to do on-the-fly model checking. And then I didn't show this, but there is some cleaning up to do with the definition here. So there are some restrictions that can easily be removed, but not in a 15-page paper. Thank you.
Questions?
Okay. Yeah, so this is just more of a clarification question. So there's also like the number of parity colors that you have, right? And does that play a role in this construction?
No, I don't think so. Okay. There's in this Kobayashi-Ong paper I mentioned is they have a result that if you go to just one parity, it doesn't change the complexity at all.
I see. Okay, so the complexity is all on the higher order recursion.
Yes.
And that sort of subsumes the complexity due to.
And so I have quite a few papers on things like that, and usually it's the higher order things eat everything else. So.
Okay.
Any other question? I want to ask a question. So if I understood this correctly, this is sufficient conditions, right? That's an example that fits.
No, it characterizes the. It's complete for K for this space complexity class. So there's an upper bound and a lower bound.
But in terms of restrictions, is that the only thing, or is there a chance for other? Because basically you're saying that you have to do tail recursion and then you deal with a parity automaton. But is it obvious that that's the only, or like is there another inhibitant with the same complexity class, like another restriction?
I think if you want to hit exactly like upper and lower bound, I think this is the way to go. So it's just simply from the analysis of this related framework. And so the idea is that the alternation you really have to get rid of, because alternating exponential space is exponential time of one exponential more. So I don't think there's really a way around this. Maybe you can cast it a little bit differently, but I think in general this is how you have to do it.
And for the theorem statement, so you sort of, again, I didn't really understand the details from a short talk, but sometimes there are things which may not be written as tail recursive, but without significant effort be converted to tail recursive.
Yes.
Does this apply to them too, or somebody has to convert? Like the factorial example you showed, is that's not a tail recursive, right? But I can change the factorial to take the value in, and then all of a sudden it becomes tail recursive.
I think you can generally do this, but often, like if you do it in a generic way, you have to go up one exponential, and then that doesn't help you at all, because, well, now it's tail recursive, but one level higher.
Asking about your theorem, does the theorem apply? It says if the HORS is like syntactically tail recursive, then the theorem applies, not if it's semantically tail recursive. Like if I take something that is tail recursive, but I obfuscate it by...
Well, if you remove the obfuscation, then it would still work, yeah. But so how do I mean, there is certainly recursion schemes that don't look tail recursive, but with little effort you can make them tail recursive.
Right, but your theorem wouldn't apply to them.
Well, after rewriting, yes. But then there
But
are
rewriting could be very expensive.
yes,
right?
but there should be a general way to rewrite every recursion scheme into a tail recursive one at the cost of one added exponential, which then complexity-wise actually makes it worse.
Right.
Yeah. So, but of course there are some that technically aren't tail recursive, but if you look at it hard enough, then
Right,
this
so
goes.
that's still, like, classifying those maybe still left open.
Yeah, maybe.
So are you talking about continuations? Like if you use continuations?
Yes.
you
Yeah.
do diff one?
Exactly. If you go to the analog of continuation passing style, it's tail recursive, but then it's also very expensive.